Hello everyone, I am Ma Zhenglu. I am from Sichuan Vocational College of Chemical Technology. Today, we will learn about the fracture and strength of polymers. Polymer fracture refers to the rupture phenomenon that occurs when polymer materials are subjected to external forces. This phenomenon involves the physical properties and chemical structure of polymers. Polymer fracture can be divided into two types: brittle fracture and ductile fracture. Brittle fracture occurs without significant deformation of the polymer before fracture. During fracture, the material undergoes little to no plastic deformation. The fracture surface is flat and shiny. It is also perpendicular to the applied stress. In the stress-strain curve, brittle fracture occurs before yielding. The stress-strain curve shows a linear relationship. The elongation at break is less than 5%. The area under the curve is less than 1. These are characteristics of brittle fracture. Ductile fracture refers to fracture that occurs after significant deformation of the material. Its main feature is the occurrence of noticeable macroscopic plastic deformation. Fracture occurs after the yield point. Fracture after the yield point results in large deformation. The fracture surface shows extensive deformation. The stress-strain curve is nonlinear. Before the fracture point, the slope can be 0 or even negative. The fracture energy consumed is large. The characteristics of ductile and brittle fracture are significant for engineering design, material selection, and safety assessment. In practical applications, how do we differentiate the fracture modes of materials? Here, we will focus on two key points. The first is to examine the location of the fracture. If fracture occurs before yielding, it is brittle fracture. If fracture occurs after yielding, it is ductile fracture. The second point is that brittle fracture and ductile fracture exhibit different fracture surface morphologies. The main difference between brittle and ductile fractures lies in their macroscopic and microscopic morphologies. Brittle fracture typically involves minimal plastic deformation. The fracture surface is relatively flat. In contrast, ductile fracture is accompanied by considerable plastic deformation. The fracture surface exhibits typical slip features. Next, we will learn about the strength of polymers. Based on the previous course introduction, we mainly discussed two aspects of polymer strength. One is the yield strength, and the other is the fracture strength. We will not go into detail about their calculation. The strength of polymers is influenced by various factors. These factors include molecular structure, molecular weight and its distribution, cross-linking density, processing conditions, and post-processing. Next, we will explore these influencing factors in detail. First, the structure of the polymer. The chemical structure of the polymer's main chain and side chains has a significant impact on its mechanical properties. The strength of the polymer comes from the chemical bond strength of the main chain and the intermolecular forces. The greater the polarity, the greater the strength. The more hydrogen bonds, the greater the strength as well. For example, polymers containing aromatic rings generally have higher rigidity and strength than linear saturated polymers. Second, the steric hindrance of the molecular chain affects the material's strength. The higher the degree of branching of the molecular chain, the greater the molecular distance. This results in weaker intermolecular forces. This leads to a decrease in tensile strength. However, the impact strength increases. For example, branched LDPE and linear HDPE show differences in impact strength and tensile strength. Third, cross-linking density. Cross-linking refers to the chemical bonding between or within polymer molecules. Cross-linking can significantly improve the material's mechanical properties. such as strength and toughness. However, excessively high cross-linking density may cause the material to become brittle. Fourth, molecular weight and its distribution. The molecular weight of a polymer is one of the key parameters determining its strength. In general, the higher the molecular weight, the greater the polymer's strength. Once the polymer reaches a certain molecular weight, the tensile strength no longer increases with the increase in molecular weight. However, impact strength can still increase with the increase in molecular weight. Molecular weight distribution is also important. A narrower molecular weight distribution helps improve the material's consistency and performance. Fifth, the aggregated structure also affects the strength of polymers. For example, the crystallinity of a polymer. Crystallinity refers to the proportion of the crystalline portion in a polymer. It has a significant impact on the polymer's strength. In general, the higher the crystallinity, the higher the polymer's strength. This is because the molecular chains in the crystalline portion are arranged orderly, resulting in stronger intermolecular forces. This increases the material's mechanical strength. However, it is important to note that the effect of crystallinity on the strength of polymers is not always positive. For example, as crystallinity increases, the material's impact strength may decrease. This is because the crystalline portion makes the material more brittle. In addition to crystallinity, orientation can multiply the strength. This is mainly because, after orientation, polymer chains align parallel to the direction of the applied force. This significantly increases the proportion of breaking the primary valence bond during fracture, since covalent bonds are stronger than van der Waals forces. Sixth, defects also affect the strength of polymers. During polymer production and processing, various defects may be introduced, such as bubbles, cracks, impurities, and so on. These defects become sites of stress concentration, thereby reducing the overall strength of the material. Seventh, environmental factors are also one of the important factors affecting polymer strength. Environmental factors such as temperature, humidity, and UV radiation can affect the strength of polymers. For example, the effects of stretching rate and temperature. The faster the stretching rate, the higher the yield strength and fracture strength. This is because the molecular chain segments cannot keep up with the external force, requiring greater external force for material yielding. The lower the temperature, the higher the yield strength and fracture strength. This is because the movement of chain segments is frozen, requiring greater external force for material yielding. UV radiation may cause material aging, thereby reducing its strength. In conclusion, the factors affecting polymer strength are multifaceted. It is necessary to select suitable materials and optimize processing techniques based on the specific application requirements to achieve the desired mechanical properties. When designing and manufacturing polymer materials, these factors must be comprehensively considered to ensure the final product meets the required performance standards. In this course, we mainly discussed polymer fracture and polymer strength. The focus was on the factors influencing polymer strength. I hope everyone can carefully master and understand these concepts. This concludes the relevant content of our course. Thank you for listening. See you next time.